Chapter 19. Really, in Chapter 19, what they're talking about is what's called the Avagadro principle, and that there's a very intimate relationship when it comes to gases. And what I mean by intimate means that they have a big effect on each other. And that relationship deals with the variables that they're showing here. When you have a small change in pressure, it has a big effect on the other variables. A small change in the volume of the container, a small change in temperature. You add some more moles of gas. This all has a big effect on things. Whereas with liquids and solids, when you're changing the temperature, for instance, yeah, you get some expansion and contraction. But again, unless you have phase change, you don't really get a dramatic change in the other variables. So they dedicate this chapter. Chapter 18 was gas laws, dealing mainly with mixtures. Chapter 19 can be mixtures or chemical reactions, but they're all dealing with Avogadro's principle, PV equals nRT. Now, the universal gas law, PV equals nRT, comes from a combination of the relationships that we were using in Chapter 18. The Avogadro law, for instance, P1 over N1 equals P2 over N2. And then we said, for instance, we could combine Borel's law, Charles' law, and Gay-Lussac's law. Gay-Lussac was P1 over T1 equals P2 over T2. And then we get the combined law, which is this right here, P1V1 over T1 equals P2V2 over T2. If we look at that instead of an initial final state, if we look at just the final state only, then we can focus on this relationship right here. PV equals nRT. All right, so a little bit of background. If they ask you what Avogadro actually said, this is what he said, that if everything else is made equal, if you have, for instance, a constant pressure and temperature, which you usually do, if you're doing a reaction in the lab, then the constant pressure is your air pressure in the room, and your temperature is the room temperature. And yes, they do change from time to time, but they stay pretty constant unless there's suddenly a dramatic shift in the weather. Equal volumes of gases contain the same number of particles, which means that because the particles are so small compared to the distances between them, we care about the mass, but we don't care about the actual identity of the particles. And so what it's saying is that this pressure-volume relationship, this energy that's associated with it, is going to be based upon the number of particles and not the identity of those particles. So Avogadro actually, what he established was what was called the molar volume. The molar volume is that if you are dealing with STP conditions, no matter which gas you're using, any gas, 1 mole of that gas will occupy 22.4 liters of space. So that's a good relationship to know, but it only works at STP conditions. All right, so what do you get then? Really, there's two types of problems in this chapter, and it doesn't matter if we're dealing with mixtures or if we're dealing with chemical reactions. Under all circumstances, we can do mixtures or chemical reactions. Under ideal conditions, the relationship among pressure, volume, temperature, and moles of gas is established by PV equals nRT. Now, again, pressure for P. Remember, V is the volume of the container. N is the moles of any gas. R is a constant. And we're going to talk about the gas law constant in just a moment. And then T has to be in Kelvin, Kelvin temperature. So we can use PV equals nRT under all circumstances to answer relationships about mixtures and chemical reactions. However, here's a shortcut. At STP, 1 mole of any gas is 22.4 liters. So there's really two things. If we're running something at STP conditions, then we're going to use this relationship, 1 mole of a gas is 22.4 liters of space, as a shortcut to having to do all this. But if we were to use PV equals nRT and ignore the STP molar volume, then we would still get the same answer. So you can always use PV equals nRT, but it's a good shortcut rather. If you know 1 mole of a gas is 22.4 liters under STP conditions. Now, STP conditions, 0 degrees Celsius and exactly 1 atmosphere. How often does that really happen in the lab? And the answer is almost never. So at the AP level, 99% of the time we're using PV equals nRT. Now, the gas law constant itself, R, the value that makes all the other values work in that relationship. The one that your book uses a lot is this 8.314 value. And the one that they use in college a lot is 0.0821. You don't have to memorize either one of them. They'll be given to you on a formula sheet. But do note that the only difference between the two of them, if you look at the units, is that if they're using kilopascal for your pressure unit, then we'll use the 8.314 value. If they're using atmospheres, then we'll use the 0.0821 value. But there's actually a whole bunch of R values, depending upon, again, certain things. Usually it has to do with the pressure unit. Again, if you're using liters, which we most commonly use, they use the 0.0821 value. However, a lot of times with gases, they need a larger volume to have any significant amount of material in it. So meters cubed, if they use meters cubed, then you use the 8.21. Really all they've done is they've taken the relationship and multiplied it by 1,000. By 100 in order to make the conversion. In organic chem, I use calorie a lot as the as an energy unit, so we tend to use 1.987 as the value. If you look at this 8.314, besides kilopascal, it's also used when we encounter joule. Now, joule is an energy measurement, and it comes from the idea that the energy being done is work energy. So force times distance, and the force would be pressure, and the distance would be whatever expansion and contraction and change in volume. So there's actually a relationship between the gas law constant and energy as well. I put a box around the 62.4 millimeters of mercury liters per mole Kelvin because that's not in your book, but it's a good shortcut. We use it in AP Chem all the time because, again, your pressure gauges are going to be measured in millimeters of mercury. So rather than having to convert the unit and then plug it into PV equals nRT, it might be better to just memorize 62.4 millimeters of mercury liter per mole Kelvin. And here's another summary. Again, the first one is the one we use in AP Chem a lot, 0.0821. The 8.314 is in your textbook because of the kilopascal pressure unit. And I always tell students it's a good idea to memorize the 62.4 if they give you millimeters of mercury as your pressure, because that's what pressure gauges are calibrated in. And again, it reminds you here that which R value do you use? You use the one that's the same unit as your pressure. All right, so what type of problems can they give you with PV equals nRT? Well, they can give you all of the information except for one of the variables and have you solve for it. So let's start with that one. That one's a pretty easy one. So let's copy and let's paste. Okay, so what are they doing here? First of all, I know it's an ideal gas law problem because it says so right in the title. But if I didn't know from the title, I know that they are giving me, they're asking for mass. And mass is normally grams, but I also know that if I know the moles I can get the mass. So they're mentioning moles. We have a volume right here. We have a temperature. And we have a pressure, PVT, and then what tells me to use PV equals nRT is the fact that we're dealing with mass or moles. So I'm going to start with PV equals nRT. Now, if I want the mass, I need the moles of neon gas. So I'm going to solve for moles. And now I can substitute in. Pressure is 1.64 atmospheres. That means I have to use the gas law constant that is associated with atmospheres. Put in my volume. All right, so that gas law constant with atmospheres is 0.0821 liter atmospheres over moles Kelvin. And the Kelvin temperature is 254 K. All right, so let's go ahead and solve for moles of neon. 1.64 times 24.6 divided by 0.0821 divided by 254. I get 1.93. Now, I can convert that to grams. Get out my periodic table. 1 mole of neon is a certain amount of grams of neon. Let's look it up real quick. Neon. 20.179 grams. So we do 20.179 times 1.93, and I get 38.9 grams of neon. Pretty easy problem. Okay, let's see what's up next. Okay, so besides that one where we have a formula and then we're solving for one of the variables, they introduced density and molar mass calculations. Pardon me. Now there's separate formulas for density and molar mass, but I'm going to approach the problem from a more conceptual way rather than using those formulas. The more formulas you have to memorize, it really hurts your conceptual understanding of the material. And then the second part of chapter 19 is gas law stoichiometry, which means the first part of chapter 19, density and molar mass, this is going to deal when we have a gas by itself or when there is a mixture of gases. So in other words, a gas by itself meaning we've completed a chemical reaction, or a mixture after completing a chemical reaction. And gas law stoichiometry is PV equals nRT stoichiometric. Well, just like thermal energy was stoichiometric. If you burn a certain amount of gas, or I should say oil in this case, if you burn oil, you get a certain amount of heat. If you burn twice as much oil, you get twice as much heat. Gas laws are the same way. If you have a certain amount of gas, it creates a certain pressure. If you double the amount of gas, the moles of gas, it doubles the pressure. So it is stoichiometric in relationships. So when we deal with stoichiometry, we have to go back to things like limiting reagent, percent yield, limiting versus excess, empirical formula, molecular formula type of calculations. So there's quite a bit in chapter 19, even though there's not a lot of notes. There are quite a large variety of different types of problems to do. So I'm going to get into those types of problems in the next video. All right, thank you very much.